Okay, so welcome to today's lecture. So today's okay, let it be. So let us look at data processing inequality. What, testing, relative, entry. Okay, good. So as we have seen earlier, like our approach to prove the data processing inequality is just to trace out a register, right? So basically, what I'll be trying to prove is that the epsilon h of row AB, some joint state on AB, with respect to another joint state, sigma AB, is greater than or equal to d epsilon h of, let's say, rho A with respect to sigma A. And we saw the background behind this, like any operation that you do. So classically, it was the private coin algorithm. Quantumly, it is our quantum operation. Okay, what we call the completely positive trace preserving superoperator. So we have defined our general quantum operation as you attach an ancilla workspace initialized to the ket0 state, okay? And then you do a unitary on the bigger system, and then you trace out the ancilla. So and then I mean you can easily see that if you attach an ancilla, then d epsilon h does not change. Okay, so let me just write it down before we actually start proving it. Like observe. So these are easy checks which you can do at home. So d epsilon h. So take some state on the system A, attach an ancilla B. And this will be sigma A. You attach an ancilla B. So you can easily see that this is equal to the original smooth hypothesis testing relative entropy, right? Okay. And I mean, this is the first operation of this in the definition of quantum operation. The next one was unitary. And again, easy to see that unitaries change nothing. So this is, so if I do a unitary on the state rho A, so this is UA inverse. So the same unitary I do on sigma A. So you can easily see that this is same as d epsilon h of rho A with respect to sigma A. Okay. Yeah, so these two observations make sense, that attaching ket0 ancilla does not change the relative entropy, the smooth hypothesis relative entropy, and the unitary operation does not change. Okay. So basically, the only thing.
So the second the second property happens because the optimizing pi in the like over which we maximize, right? That is still the same, because the unitary essentially does not change the trace. So we can use
No,
the
so the
same
so the
pi.
pi also, the optimizing pi changes by the action of the unit, the conjugating action of the unit.
Right, right. So it becomes u dagger pi u or something, right?
The same u pi u dagger,
U pi u dagger.
same thing. Okay, so essentially, I mean, one way, I mean, this is, I mean, it's correct. I mean, it's the intuitive way of saying it, but I mean, when you formalize it, it will just come down to what I just said, like conjugating by unitary. So applying a unitary transformation is like a change of basis, except that it's a change from one orthonormal basis to another. And the way the definition of the hypothesis testing entropy has been set up, I mean, yeah, you can see that. I mean, it is basis invariant. Yeah, in some sense. I mean, this is the intuition, but of course, the formal proof is you take a unitary, you have conjugated your states, and you see that the optimizing pi is the same conjugated pi. So if let us say some particular pi hat was the optimizer for the original semi-definite program, then u pi hat u inverse is the optimizer for the new semi-definite program. And then a similar thing if you attach an ancilla zero, right? So you can figure out what is the optimizing pi. It will be the new optimizing pi will be the old optimizing pi tensored with ket Brazil. So okay, and then there are, I mean, things to argue that indeed this is the optimizing pi and you cannot do it better. But I leave it for you to think a little bit and work it out. Yeah, so you have to give it a little bit of thought to make it absolutely rigorous that this is how the optimizing pi looks. But I mean, you already know what. That's not so difficult. Uh, some more doubts before we proceed with the tracing out thing. Okay, so let's get back. So now, the only thing which can decrease the smooth hypothesis testing relative entropy is the trace out operation. Okay. So now let's prove data processing. So
I sort of have a like slightly look ahead question, but are there any non-trivial states? I mean, not tensor. There's any non-trivial states where trace out does not decrease things? I mean, explicit examples, no, I mean.
you mean non-entangled states or something?
Now, suppose, I mean, you have a rho AB and rho AB
No,
sigma
no,
AB,
yeah.
and you trace out B, but the hypothesis testing entropy does not decrease. But rho AB and sigma AB are not product states.
Yeah,
They are,
I believe there are. Yeah, I mean,
okay.
so I mean, it's. I mean, these are specifically tailored rho AB and sigma AB.
Okay. Okay.
So yeah, that's an interesting question to give it some thought. So of course, I mean, you want an entangled state for that, or whatever, a non-tensor product state. Let's see. So yeah, I would guess there are. So I mean, you can even see it classically. Okay. So classically, yeah. So maybe it's easier to see it for the Shannon relative entropy that this holds. Okay. And then yeah, and then the same example would actually work for the d
Quantum.
epsilon h also.
Right. Right. Okay.
So let's see. Yes, so I mean, we have seen the proof of this in the classical world. So it's basically the same proof in the quantum world. So what was d epsilon h rho a with respect to sigma a? So this was max over this p of m in pi a, which is between 0 and identity. and trace of rho pi is larger than 1 minus epsilon. And I want to maximize this, so negative log of trace of sigma pi. Right? This was a definition of the hypothesis of relative entropy. Now, find the optimizing pi for this, and now look at this problem. Okay, so, or rather, right, so d epsilon h rho ab. Okay. So whatever it is, it will be larger than any feasible thing. So what I'm saying, so find the optimizing pi. So let's give a name to the optimizing pi. So optimizing pi is pi hat a, let us say. So all I'm saying is that sigma AB times pi hat A tensor identity. Okay. So basically, so pi hat A tensor identity on B. So this is a POVM element in the system AB. So this is between the zero operator on AB and the identity operator on AB, as you can easily see. So for example, I mean, you can see what are its eigenvalues in this tensor basis. Okay, to see that. So the eigenvalues in the tensor basis are the products of the eigenvalues of pi and identity. Now the eigenvalues of pi are all between 0 and 1 because of this operator inequality. Okay, and multiplying it by the eigenvalues of identity on B is just multiplying by 1. So I know what the eigenvalues of this are. So these eigenvalues are the same as the eigenvalues of pi, but there are multiplicities. Each eigenvalue gets repeated dimension B times because of this. But that's fine. So whatever it is, it's between 0 and 1. So
But anyway, pi is a it's not a project. Okay, sorry.
So so first of all, I've seen that this is a POVM element. Pi hat A tensor identity B. And now again by the property of partial trace, you can check what is trace of rho times pi hat A tensor identity B. Right. So by definition of partial trace, this is trace of this should be rho AB. Okay. So this is trace of rho A pi hat A. Right. This is the one of the ways of defining partial trace here. And this I know is larger than 1 minus epsilon because this pi hat A was the optimizing pi hat A. So the optimizing pi hat A has to satisfy this constraint. Okay. So this is larger than 1 minus epsilon. So what I've shown is that this new POVM, now this is the system AB, pi hat A tensor identity B. It satisfies all the constraints. Okay. It's a valid POVM element, and taking the trace with rho AB gives me something larger than 1 minus epsilon. Okay. And now if I evaluate this quantity, this objective function, so whatever its value is, it will be less than d epsilon h. So d epsilon is obtained by optimizing over a general POVM element on AB. This general POVM element in general will not be of this tensor product form. Okay. So that's why we get the inequality. So I think, yeah, so that's it. We are done. Any questions about this proof? No? Hari, are you on board?
Yeah.
Yeah, good. So you can see how easy it was to prove the data processing inequality for d epsilon h, whereas we still actually haven't managed to prove it for d, the Shannon relative. So we'll go there. But before that, let us do some.
Did we like do anything similar in the classical case for the
Yeah.
smooth
This is the same as
entropy?
the classical, except that
Yeah,
we are
okay.
using quantum notation.
Yeah, okay.
So yeah, I mean there are striking parallels. I hope, I mean, that you can see between the classical part of the course and the quantum part of the course. But you need the right notation and the right mathematical tools also to push through. There are also striking differences, like the condition entropy becomes negative. Yeah. So, but again, I mean, we are trying in the one-shot quantum information that we're doing. I mean, we're trying to reduce everything to some simple elementary principles, and we will derive everything from there as well.
Pranab, I have maybe a repeat question from before, but so the way we have described quantum operations, you purify, then as in you add an ancilla, then you do a unitary, and then you trace out.
Correct.
So these things essentially subsume all of classical also, obviously. But
yeah,
does that mean that, so if I take, let's say, if I have a distribution, if I have any distribution, and I define a function on the support of that distribution to the support, but essentially what I'm doing is I'm rearranging, I'm defining some function which let's say it's not 1 1, it's some arbitrary function that I come up with, and it rearranges the mass on the image of the function. Okay, so even such arbitrary functions can be described using this formalism.
So functions means it's a private coin algorithm. The function tosses his own coin and then does a deterministic computation. I mean, I'm just asking what kind of functions you are saying.
1 second, just 1 second. Yeah, can you hear me now?
Yeah, I could hear you before also.
Oh,
yeah.
okay. No.
So
I was saying that, I mean, even if I come up with any arbitrary deterministic, not even private coin, if I come up with some deterministic function from the support of the distribution to the support of the distribution, I'm just rearranging the mass.
Yeah.
So even these things,
even that comes into it. So we have seen the proof of that in the classical part of the course, that any deterministic function, you can write it as a Boolean circuit.
Right. You can turn it into a bijection.
You can turn it into a bijection, and we saw all that, right?
Yeah, right. Okay. So, but it's even more powerful. And I mean, I'm just thinking it's even more powerful because your function can even be not a function in the classical can not be a function in the usual sense, but can be a randomized function, as in it maps elements to a distribution.
Correct.
Maybe. And even then it works out. That is what you call private coin.
Private coin algorithm. Yeah, I want to emphasize the word private coin. I mean, the function can toss its own coins and then do a deterministic operation.
Right. Okay, I see. Okay, thank you.
Which is exactly what you said. Like, if you feed it in if you feed a sample point X, you get a probability distribution on the output symbols Y. Okay, which depends on X.
Right. Exactly.
Okay, but it only depends on X. That's what the private coin means. If I feed in the X prime, I get some other distribution on the output symbols Y. Okay, which depends only on X prime.
Okay. So I'm
no more constraints other than this. I am not saying how difficult it is to create the probability distribution or how many gates you require. Nothing like that.
So I have so this is where I always get confused. So suppose I have a distribution. Okay, let's say P and Q, and classical. Let's take classical. I have a distribution, and P and Q, and P is any distribution and Q is also any distribution. And I'm looking at the hypothesis testing entropy between them.
Okay.
Now I do the following operation on P, or on maybe on both of them. Okay, it doesn't matter. Maybe on both of them. And the operation is, I'm going to randomize over permutations. Essentially, I mean, this might be a little weird to hurry, but I'm going to do the classical analog of a design. Okay. So that will turn each of the distributions into the uniform distribution.
Sure.
But my question is that, is this mapping that I did, is this a mapping from the support of the distribution to the support of the distribution, or is it a mapping from distribution space to distribution space?
So So, I mean, in loose notation, we will call it mapping. It's a private kernel algorithm mapping the support to support. But of course, formally speaking, it is mapping input distributions to output distributions. Okay. But the question is, how is the mapping done? The mapping is done by sending a single sample point, which is basically a delta distribution. Okay, to a probability distribution on the output signals.
What I did not understand. Sorry.
Yeah. Okay, I'll repeat. I mean, I'm not saying anything great. So this map from input distributions to output distributions is of a particular form. Okay. It is obtained by sending a sample point at the input to a probability distribution on the output signals.
I see. Yeah.
A sample point of the input is a delta distribution where all the mass is concentrated on X.
On one guy. Yeah.
Okay.
Yeah.
But you feed in this delta distribution the input, what you get at the output is not, is some distribution. It's not a delta distribution.
Yes.
Okay?
Yes.
A deterministic algorithm, if you feed in X, will output some fixed Y of X. Okay. The deterministic function also maps sample points to output distributions, but those are delta distributions.
Yeah. I see.
Yeah.
Okay.
Yeah. So, is that clear to you, Hari? Also.
Yeah, slightly.
Yeah, I mean, this is just notation. I mean, it is. Yeah, the summary is a classical private kernel algorithm takes as input a symbol X, okay, and outputs a probability distribution on the output symbols, which we normally write it as P of Y given X. So this distribution is sensitive to X. That's all.
So can I write any? So I mean, this is the heart of my confusion. Can I write any function which maps, say, distribution, that the domain is a distribution space, not the support. Okay, the domain is a distribution, is a higher order thing, to another distribution space. Can I sort of turn any such map into a function, into a private kernel algorithm from the support to some distribution?
No. I'm not saying that. I'm not saying that a function from input distributions to output distributions is of this form. Okay. So, in particular, the form that I'm talking of forces linearity. Like if I supply the input distribution, which is half of x1 and half of x2, the output distribution will be the half of probability of y given x1 plus half of probability of y given x2.
I see.
Okay. So the linearity comes in. When I'm talking private kernel algorithm, by their definition, they are linear. Okay, so they're linear in the space of input probability distribution. So the input probability distribution is for vector space. Okay, and
okay. I see.
Yeah, in the sense that any convex combination of two probability distributions is a probability distribution. So it's it's limited vector space in that sense. Okay, and private kernel algorithms are linear maps. Okay, from input probability distributions to output probability distribution.
Yes. I see.
Every linear map from input probability distribution to output probability distribution is of this.
Yeah, because I can. Now I understand what you say. You're basically saying the following: that okay, maybe formally it seems a little weird. Formally, I'm giving you a function which is mapping, whose domain is actually distributions, not support, and it is mapping also to distributions. But suddenly, if I impose linearity, what I can essentially do is I can think of single points in the support as a delta distribution in the domain of this map, and then I can take a convex combination and do the same thing. But this necessarily requires linearity. I see. Okay, thank you. Thanks a lot, Pranav. This clears up a lot of things.
Yeah. Okay. So yeah. So there is. I mean, now maybe if you go and look at the abstract way of defining quantum operation, you see why they are insisting on linearity. Okay. So yeah. So but the way I've defined a quantum operation, you can check that it's linear in the space of input density matrices. So, right? I mean, simply write it down.
It has to be. It has to be.
Quantum It's an important point. Okay.
I think maybe I mean you obviously got my point, but I think Hari might be a little confused because he doesn't know where.
Yeah,
this
no,
dot
no.
came
So
from.
I'm writing it down. So the quantum operations that you have defined are linear in the space of input density matrix. So T is a quantum operation. Okay, quantum operation. So what I'm saying is that T of let's say alpha 1 rho 1 plus alpha 2 rho 2. Okay, so this is alpha 1 T rho 1 plus alpha 2 T rho 2. Of course, I mean, for this to make sense, rho 1 and rho 2 are density matrices. Now, alpha 1 rho 1 plus alpha 2 rho 2 also be a density matrix. So this only happens for convex combination. So this is when 0 less than alpha 1 alpha comma alpha 2 less than 1 and the sum is 1. Okay. So now you can check that alpha 1 rho 1 plus alpha 2 rho 2 is also a density matrix. So it's obviously Hermitian. It's also positive semi-definite because I'm adding two positive semi-definite matrices. We checked that before. Okay, and it is trace 1 because alpha 1 plus alpha 2 is 1. Okay. So the input to T out here is a density matrix. Okay, if this density matrix is a linear combination of density matrices rho 1 and rho 2. Okay, so this is also a density matrix. Correct. Okay, and the same alpha 1 and alpha 2 come out here. So this is the linearity. Okay. And remember how was T obtained? So T was obtained, just to remind you, by attaching ancilla some Cadbran 0 on some ancilla space, joint unitary, joint unitary, joint unitary on yeah, on system plus ancilla. And finally, trace out of ancilla. And again, you can now formally check that all these operations are linear in the space of density matrix. Like if I take rho 1 and rho 2, okay, so and my operation is send rho 1 to rho 1 tensor Cadbra 0, send rho 2 to rho 2 tensor Cadbra 0. Then you can check that alpha 1 rho 1 plus alpha 2 rho 2 and just tensoring it with Cadbra 0, and I'll use the distributive property of the tensor product. So this is nothing but alpha 1 rho 1 times Cadbra 0 plus alpha 2 rho 2 tensor product Cadbra 0. So like that. And even the joint unitary, right? So if I conjugate the alpha 1 rho 1 plus alpha 2 rho 2 by some unitary, okay, that means I multiply on the left by u and multiply on the right by u inverse, then you can see it's linear. I mean, this is the same as alpha 1 u rho 1 u1 inverse plus alpha 2 u rho 2 u2 inverse, which is what the right hand side is. And similarly, trace out. So we have seen that the trace out operation is also linear in the space of the vector space of matrices. Okay. So the quantum operations, as I have defined, are automatically linear over the space of density matrices. So this actually answers Shayantan's question in the quantum domain. Like, of course, you can like imagine the space of all functions from density matrices to density matrices. But not all functions will have this form. In particular, not all functions will respect linearity of the input. Okay, so we are only interested in functions from density matrices to density matrices that are linear in this sense. But then there are more conditions. So classically, I mean, you can define a private coin algorithm abstractly. So that's basically where Shaitan is coming from. So classically, you can define a private kernel algorithm as look at the space of all functions from probability distributions on the input sample space to probability distributions on the output sample space. Out of these functions, look at linear functions. Now, these linear functions are exactly what I call private kernel algorithms. And the proof is, to describe a linear function, I only need to describe its behavior on an individual sample point. So that's individual sample point means it's a delta distribution on the input space. So, and that's enough. Well, once I have the description, everything else is known. Okay, so one can take a similar abstract view. Said, okay, look at the space of all functions from density matrices on the input space to density matrices on the output space. Okay. Now, not all of them will be linear. So there's a subset of which is linear. Are these precisely the quantum operations? So here, okay, so I mean, before I answer this question, is this making sense, Hari?
Yes. So like we are saying that from the map of from the family of functions mapping from one distribution to another, linear functions are called, the
other private kernel algorithms.
Private coin algorithms are.
Yeah.
So are they defined? So is it like defined that private coin algorithms are defined as the linear functions, or is it?
Well, historically, no. Historically, private kernel algorithms were how I defined it in class. Like the algorithm is some circuit or whatever computer which is tossing private coins, but abstractly now you can define it this way.
Yeah.
Okay. So yeah,
I mean,
but
I maybe I can make a comment if after Pranav finishes.
Yeah. So so I'm saying that, but maybe I mean at this advanced level in the course, it's good to know the abstract viewpoint that private core algorithms are mathematically very natural. I mean, they are the linear functions from input probability distributions to output probability distribution. Precisely that. Okay. So I mean,
Can it be formally like proven that?
I told you the
all
proof.
the linear.
I told you the proof that to describe a linear function from input distributions to output distributions, I only need to describe its behavior for the delta distribution, because any input probability distribution is a linear combination of that, right? It's a convex combination of delta.
Deltas,
So the same thing holds out here. Like, so let us say I look at all functions from input density matrices to output density matrices. Now I want to only look at the subset of linear functions. Okay, so to understand the subset linear functions, I only need to describe its behavior on pure states, because every density matrix, as you've seen, is a convex combination of pure states, right? So to describe a linear mapping, okay, it suffices to describe its behavior on all the pure states, and then the rest goes well. So that is also there. So sure. So you can say that great. Like so I will not talk of linear maps from density matrices. I'll just say that, oh, take a pure state and send it to an arbitrary density matrix. So that's what you were doing classically. Like take a sample point, send it to some arbitrary probability distribution on the output signals. Okay. So do it for every sample point, and you get your linear map or private kernel algorithm. So can I do the same thing out here? Can I take, of course, now there are infinitely many pure states, but that's fine. I mean, everything still makes sense. So, take a pure state, send it to an arbitrary density matrix, okay, on the output Hilbert space. So this automatically defines a linear function. Okay. So now the So now this I should mark. I mean, I should not say that this does not automatically define linear function, because you need consistency, right? I mean, so let us say I take some. So let us say I take, in a sense, some linearly independent pure states. So I mean, one is to, if to formalize it will take us a little bit out of scope, but we can formalize it. So I know every density matrix is a convex combination of pure states, but if I take this viewpoint, then I have to look at the set of all pure states. But the set of all pure states is huge, right? I mean, basically for every unit vector, more or less, there is a pure state. So, but it turns out that I can further reduce my space under consideration and only look at the so-called linearly independent pure states. Okay, and let us say I send every linearly independent pure state to a density matrix. Okay, does this define? So obviously this now defines a linear operation, but is this a quantum operation? I mean, is this something that I can obtain by ancilla 0, joint unitary and trace? The answer to that is no. Okay, but so this is where it becomes interesting. Answer to that is no. You need to put in further conditions. So just linear maps are not enough to define quantum operations. So let me, since we have come to it, I mean, if you do further reading, so I'll tell you what you have to look at. What are the complete? I've lost my pen. Okay, so let me write it here. Okay, so what was the thing? So linear maps from probability distribution to probability distributions. Okay, so this is equivalent to private coin algorithms. Okay. When I say equal to private coin, this is different historically, like you toss a private coin in. Okay, but so now the question is linear maps from density matrices on A to density matrices on B. So the question is it equivalent to quantum operations? So here quantum operations I have defined by the three-step operations, the quantum operations. So here I have defined it by the three-step process. So the question is, do linear maps define the quantum operation? The answer is no. So actually the answer is, I mean, the quantum operations are a proper subset of this. So this is the answer.
So you need to respect positivity and those things, right?
Yeah. So that's where it comes. So the jargon also calls quantum operations. So I'll tell you what the answer is, but I'll not define those concepts. So quantum operations. So we have so basically what I'm asking for is there an abstract linear algebraic characterization of quantum operations? Okay, similar to the abstract linear algebraic characterization of private kernel algorithms. So the answer is yes, but it's more sophisticated. Okay, so quantum operations are what are called CPTP maps. So completely positive trace preserving, okay, maps. So this is also called CPTP, completely positive trace preserving. Yeah. So what does this mean? So of course, I mean, they're linear in the space of density matrices. Then they have to trace preserve. It means that if I feed in a density matrix, that means it has trace 1 at the input. At the output also, I should get a density matrix, which has trace 1 at the output. So all this is nothing unexpected. This is exactly what I would get by this recipe. Like find a set of linearly independent pure states and assign them to density matrices arbitrarily. So if you do that, and the rest you extend by linearity. Okay. If you do that, you'll already get trace preserving. You'll also, okay. Now what does the word positive here mean? Positive here means that if I feed in a density matrix at the input, I should get a density matrix output. Again, you'll say, what's the big deal? Like I've taken my strategically chosen set of pure states the linear independent pure states, assign them to density matrices. The linear independent, so there is no inconsistency, and then extend everything by linearity. So of course, if I feed in a density matrix as the input, then I get a density matrix in the output. Okay, so it's trace preserving and positive. So far so good. The catch comes in the word completely. So completely means the following: like I take this abstract function from density matrices to density matrices. Okay, so this function is it's a linear map from density matrices on A to density matrix on B. Now let me consider density matrices. So let me take another system C, different from A and B. So I can think of density matrices in the joint system AC. Okay, so let me give a name. So linear maps, let us say L. Okay. So now I can ask what this means. So L. So remember, L is density matrix on A to density matrix on B. That's what it does. Okay. So sometimes, I mean, these are called super operators just to emphasize that they're mapping density matrices to density matrices. In other words, they're mapping operators to operators. So that's so to emphasize this point, that sometimes this L is called CPTP super operator. And now I tensor with the identity linear map or the identity super operator. So what is this doing? So first let me write down the condition. Now take any joint density matrix on AC. So this should be okay. So what is I doing? So let me write it out here. I is the what is called the identity quantum operation. So IC. So what does IC does? It just sends a density matrix in the system C to itself. So this is the definition. Okay. So now what is this thing saying? I have a map which sends density matrix on A to density matrix on B. It's linear. It is trace preserving. It sends density matrix to density matrix. All this is fine. Okay. So A to B. But let me tensor it with the identity super operator. Then, like, I mean, if there is any sense in mathematics, then take this map and apply it on an arbitrary density matrix in the system AC. Note that this in general is an entangled quantum state. Fine. So you apply it, okay, and the result should also be a density matrix in BC. But unfortunately, that does not happen. If I only had positive and trace preserving, there are examples of positive and trace preserving L such that after tensoring with the identity quantum operation, okay, and then applying it on a certain entangled state rho AC, what I get is no longer positive semi-definite matrix in BC. I just get a Hermitian matrix in BC, but that's not positive semi. So these things can happen. So now I have to further restrict the linear maps to be completely positive. That means the linear maps L, which further satisfy this extra property. So once you do that, then what you get is all the quantum operations. It's if and only if after that. Okay, but this is, I mean, next semester, if I teach it the quantum analog of this course, the fully quantum analog, then we'll do all these things. Okay, but right now, I mean, this is just to tell you that linear maps from density matrices and density matrices are strictly larger than the set of allowed quantum operations. So the additional property you have to add is this completely positive. So if you add that, then you. So the answer is a little more sophisticated. Yeah, any questions, Hari? A little abstract thing, and
I have questions.
you have questions, but let's wait for Hari first.
Yeah,
I'm sure Hari has more.
So, yeah, I mean, yeah, I got an idea of what this is.
Yeah, I mean, if you're wondering what this is, remember, see, density matrices or whatever matrices in general form a vector space, right?
Yeah, yeah.
So yeah, so this is a vector space, and this is an operator on the vector space, and we have seen what is the Kronecker product of operators. So it is that
Yeah,
Kronecker product.
yeah, yes.
So it's kind of, yeah, I mean, really abstract. But yeah, the point is this formulation is related to deep questions in the foundations of physics. So physicists have asked, I mean, is this the best that nature can do? And I mean, so they have asked questions like, why is linearity important? For us, I mean, for us mathematical bounded people, linearity looks like a nice mathematical property to have. But we say that, I mean, why should nature be linear? And they have some understanding, like, I mean, if you don't have linear, then the physical laws apparently become really weird. So they say that, I mean, if you need reasonable physical laws, then you need linearity. So that's one answer. Okay, and then the question is, okay, why do you need positive trace preserving? Okay, so then again, I mean, there are similar answers. Like, I mean, because trace is related to probabilities and all. Like, I mean, you have to preserve probabilities. There's no loss of information in the overall universe or something. So it has to be trace preserving. And the question is, why should positive semi-definite matrices go to positive semi-definite matrices? They've even asked that question. So they have said that under reasonable assumptions of what, I mean, I want to describe physical reality by a mathematical object. So under very reasonable assumptions on what would be a good description of physical reality, the positive semi-definiteness gets thrown in for free. I mean, they're beautiful mathematical theorems that you need a Hilbert space structure and you need a positive semi-definite and all that. Okay, so these are all foundations of quantum mechanics. So you need positive trace preserving. Okay, and linearity. So from very reasonable assumptions on what. So remember this general physics. I'm not assuming just quantum mechanics. I'm talking of what any reasonable physical law should be. Okay. So any future theory that goes beyond quantum mechanics, hopefully, I mean, will still give rise to these kinds of operations. That's the idea. And the completely comes because of this. That they say that, I mean, if I have physical process going on, okay, from A to B, and on the side there is another system C where nothing is going on. Okay, then I mean, and now if I start off with an entangled state, it very well be the system is entangled. So what I should get at the output should also be a valid quantum state. I mean, it cannot stop being positive semi-definite. If I choose not to do something on the C part and I only concentrate my attention on the A part. So this is also something which is reasonable physically. So the moment you force this, then you get quantum operations. So these are abstract ways of justifying quantum operations and gives us some confidence that this is like even very general physical theories, okay, will have to fall into this ambit of quantum operations. Yeah, Shantan, you can ask your question.
Yeah, so when we were doing the classical analog of this theorem, that you take linear maps and you're set, but somehow automatically that sort of ensures, because everything falls under this schema, that construction in the classical domain automatically sort of ensures that those maps are CPTP, right?
Correct.
So is that because of the inbuilt basis structure? Because when I'm defining the classical maps, it's like I'm defining point by point, but that essentially means that I'm defining everything on one single basis, and that is a standard basis. I don't have to care about every some general basis in the set of all unit vectors. My basis is fixed, and that is fixed by the classicality of the thing. Is that the reason why?
Yeah, of course. I mean, because in the classical computational basis, okay.
Right.
So I mean,
Yeah.
they are diagonal density matrices. So if you only
Yes.
had diagonal matrices hanging around, then you'd have got completely positive for free.
For free. Oh, okay.
I mean,
Yeah.
once you had positive, like, I mean, I'm sending probability distributions to probability distributions, which basically means I'm sending delta
Diagonal to diagonal.
distributions or sample points to probability distributions. Okay. Once you have that, yeah, then you automatically have positive trace preserving, and then the completely comes for free if you have diagonal density matrices. This whole
I
mess
see.
occurs because there are off diagonal elements. Okay? Even the example which violates this thing, that I mean, here is a positive trace preserving map which is not completely positive. So if you see the row AC which violates it, it has severe off diagonal entries.
Okay. So I just have another question. So related, I just remembered something. Sorry if I'm wasting time, but you made a comment just now that there is a physicsy reason of sort of considering these guys, that if I'm doing an experiment and I start off with a system which has
It's
some.
not just an experiment. I mean, any general evolution of systems, physical systems, will have to fall into this framework.
Okay, so it's like if I remember this comment from Shen and Kitaev that they do this. I never understood that comment. So they said that if you do this, essentially what you want is that somebody sitting in some distant galaxy should not be able to change the fact that if you just consider the action on your end of the thing, nothing will go wrong. It's not like somebody in some galaxy entangles with your system and just because of that physics goes wrong. That
Yeah. I mean, already experiments are showing that, I mean, entanglement is a real thing, and I mean, and its effects are there over large distances. Okay? And quantum theory, I mean, does not put any distance limitation on entanglement, and as far as we have been able to measure sitting on Earth, I mean, if you create two particles that are entangled and then send one off to one side of the Earth, the other to the other side of the Earth, they still remain as entangled as before. Okay, so these experiments have been done, and that is why. So the formalism here, like rho AC, it does not specify how close or far A and C are. Okay.
I see.
So
Okay.
so if you take so if you accept that there are entangled quantum states, I mean there are entangled physical states. Okay. And I mean A and C can be close or far, but these entangled things are there. And if you want something like this, if I'm doing nothing on C, then I mean if I'm doing everything on A, okay, so the
C
output
should
should
not
also be a
affect
valid
A.
quantum state, because I mean this looks like a physical process that must be occurring all the time, that something is not occurring in C and something is indeed occurring in A. Okay. So then whatever you get, the output should be valid physical description reality. In other words, it should be a valid quantum state. In our formalism, it should be valid density matrix. So this is also a very reasonable thing to have. Okay. And the mathematically interesting point is that, I mean, you have to add it as an extra action. So to get
The
that
math is sort of math is clear to me at least. I mean, but they have done experiments and checked that this sort of thing actually holds.
Yes.
Okay.
Like various predictions of this quantum theory, of this formalism, have been tested over the years to extremely high accuracy.
But is it not possible that some other theory implies the same? It's just your
Sure.
assumptions are different. That is possible, right?
That is possible, but so now, I mean, when you talk of foundational question, you ask any more general theory, it should satisfy some reasonableness conditions. Okay, this is just our feeling. I mean, maybe it doesn't. Okay, but if it satisfies the reasonableness, I mean, there seem to be good reasons that it should satisfy all these reasonableness conditions. So if you satisfy that, so these are the minimal assumptions, then all this gets forced, completely positive trace present.
Okay.
So this is something in a sense beyond the standard quantum mechanics.
Okay, I see.
Yeah, but anyway, I mean, for us, our interest in information theory is this concrete definition of quantum operations, which will be. Yeah, Hari, questions before we actually move to a Shannon theoretic topic?
Yeah, this is fine.
Okay, so let's now we have defined all these entropic quantities and so let's do something. So let us really do some information transmission. Okay, so this is point 2 point quantum channel. Transmission. Classical information. What do I mean by this mouthful? Okay. So let's draw a picture. So I have a quantum channel. So quantum channel is just modeled by a quantum operation, right? I mean, classical channel was a private core algorithm, what was called a stochastic map. So this is a CPTP map, quantum operation. So the quantum operation, of course, so at the input, so I'll call the input Hilbert space as A. Okay. So these are qubits in the input Hilbert space A. Some quantum operations of physical process goes on, and the output Hilbert space is B. Okay. And this channel, let us say, I will denote it by, is often denoted by the calligraphic N. It's a channel from A to B. So in other words, so let me write it down once and for all. So, so how is this thing coming? So NAB applied to a density matrix rho A. Okay, so this is obtained by first, I will tensor A to some ancilla. Let us say ancilla 0 on some system C, and then I'll apply a joint unitary on AC. Okay. And then I'll trace out for kind of heavy notation, I'll call it C prime.
Trace out CE because unitary from AC to BE.
Yeah. So
technically, yeah, but
so let's write what the unitary is from. So the input system is AC, but so essentially, let's say A was 5 qubits, but maybe B is 15 qubits in the output. Okay. So then where the remaining 10 qubits coming from? That's coming from the workspace. So but maybe the workspace is even larger. So let us say A is 5 qubits. I put in 20 qubits of workspace. So now AC is 25 qubits. And now, of course, the unitary will not change the number of qubits, will not change the dimension of the space. So the output is also 25 qubits, but now I'm repartitioning it into 15 plus 10. That's what Shayantan is saying. So that is what he means by the unitary is from AC to BE. Okay. So if you do it that way, then I should trace out. So this is how the channel is defined. Okay. Is this clear, Hari?
So the quantum operation is this transmission rho A cross.
Yeah, the entire transmission is described. It's a quantum operation by this 3-step process. Okay.
Okay.
So C is, let's say, 20 qubits, B is 15, and E is 10. Okay. So channel specification.
So in the classical case, we don't do this extra register adding and stuff.
Classical case, I mean, a classical case, if you are going from 5 to 15, I mean, you can sort of say that we actually do it. Okay. So, I mean, if you look at the detailed viewpoint, then if I'm going from 5 to 15, so 5 is the input, 15 is the output, then you need workspace, you need space for your private coin, right? To implement all that.
So,
so typically, A is the input, B is the output.
A and B are the messages, right? I mean, are the messages or
the message
codes?
is coming later. Message will come later. Message is the actual clear text that I want to send.
Yeah. Okay.
Okay, but right now I'm just describing the channel. So the channel is a box which comes with some specification that input is 5 qubits, output is 15 qubits. Let us say. Okay.
Okay.
And the question is, what is the channel doing internally to do this transformation?
Okay.
So internally, it will add workspace. Otherwise, it cannot go from 5 to 15. But in general, it will add more workspace, okay, to ease its operation. And this happens even classically also. So this more workspace is C. So it has added 20 qubits. So now overall, the internals of the channel are working with 25 qubits. Okay. So it has added this workspace of 20. Then the internals are this new AC. So it's doing some unitary operation on this 25 qubits. And then after the unitary operation is done, it treats this 25 qubits, it it takes a different split, like 15 plus 10. Okay, and it says that okay, the first 15 are supposed to be the output, so that will go out to the output wire, and the remaining 10 are discarded. So that's what is the remaining 10 here are discarded. So the same thing is occurring classically also. You typically have to put in more workspace than naively required, but that's fine.
See, when you put in workspace, you have this essentially classically you're turning it into a bijection, right? So your bijection is
so classically the workspace is into two parts, like the scratch space, which is initialized to 0, and the private coin space.
Yeah. So that private coin space is the extra qubits that C can. So C is like scratch plus.
C is both scratch plus private coin, but in the quantum world, we don't have to.
We don't have to do that. Yeah.
Yeah, we don't have to put a private coin. We don't have to put a probability distribution in any part of C. Okay, because we can generate those probability distributions as we have seen by unitaries and then control NOT gates and all that. Okay, so all that is required is just scratch space initialized to 0. Okay, so this will include workspace. This, if required, this can also include private coin space. It can include whatever. So is this clear? I mean, what is the internal working of this box?
Yes.
Yeah. So yeah, maybe somebody, I or Shantan, will use a jargon. So there is a name given to this unitary to realize the channel. So this is fancy name. It's called the Stein spring, named after a mathematician, Stein spring dilation. Basically, this. Yeah. Okay. So fair enough. So now let us see how one is going to use this channel for transmission of classical information. उसका हिसाब मेरे को दीजिए और उसी हिसाब से हम कभी आपका ये ट्रांसफर कर गूगल पे से तो एक काम कीजिए ना, वो पहले वो हिसाब आपने अगर कोई बिल बनाया है तो बिल को मेरे को व्हाट्सएप पे भेज दीजिए। आपके व्हाट्सएप है? तो हाँ, तो मेरा ये व्हाट्सएप ही है, तो आप इधर पूरा बिल ना कितना बॉक्स है, एक बॉक्स में कितना है और उसी और आफ्टर Okay. So now I want to use it for sending a classical message. So this classical message, I can treat it as a number from 1 to 2 to the r. Okay, I'm writing 2 to the r because I'll say r is the rate. Okay. So this classical message, it's a classical bit string. It has to be converted to a quantum state. So that is done by the classical to quantum encoder. So there is this encoder. So let us say this classical message is stored in a register M. So this encoder will map from the M space to A space, but it maps a classical bit string. So it's basically like a sample point, okay, to a density matrix. So and more explicitly, it will map M to some row M on the system E. So this is the operation of E. Okay, and now this N acts on the input state, okay, which happens to be row M out here, and at the output it creates a density matrix. So once N acts on it, so let's give some name for this. So this is row B on M. So note this notation. I mean, I've put in this M here to show that it's sensitive to the classical message. Okay, and the superscript here says on what Hilbert space it lives. So this is on the input Hilbert space and the output Hilbert space. And now this will go through a decoder. Okay. So the decoder is also a CPTP map. So let us say and the output of it will be classical. In other words, the the output will be a probability distribution on some symbols. So the alphabet is the same, because I know that the input alphabet of the message is from 1 to 2 to the R. Whatever output is, it's a probability distribution from 1 to 2 to the R. So it will be m hat. Okay, and so yeah. So let's give a name. So this is B to m hat. So that's what the decoder does. And what I get here is a probability distribution on m hat. Okay. So note that the encoding was classical to quantum. The decoding is quantum to classical. So essentially, it's like a measure. Okay, so there was this quantum state rho b m out here. A certain measurement was done that created probability distribution on the output symbol. So let's say this goes through D, and then what I got is so let's give a name for it. So it's a probability distribution on m hat given a. So this is the entire process. And what do you want? I mean, if it is really transmission of information correctly, what I want is that for every little m, okay, for every message m that could be transmitted, if I run through this entire process, this probability distribution which I get, okay, is highly concentrated on m. So basically, what I want to say that so this is what is called the correctness requirement. Correctness. So probability m hat. So I want m hat to equal m with high probability. Probability of m given m is larger than 1 for all. This is the correctness requirement. So is this clear? The setup for transmission of classical information. So the classical is classical information because the m here is classical.
The decoder is just a measurement from
The decoder is
quantum
basically a
space to
measurement. I mean, the decoder is any quantum operation whose input can potentially be any density matrix in the system B, but the output should always be a probability distribution. So this is just, I mean, another fancy of saying that decoder is a certain measure. I mean, measurements abstractly are probability measurements abstractly. I mean, the most general measurements are quantum operations that send quantum states to probability distributions.
yes. That's clear.
Okay, so this is the setup, and the question is, the channel N is given to me. The channel N is a box, your whatever instrument, it's your optical fiber or something like that. So channel has its characteristics. The question is, what is the best encoder and the decoder I can construct for this channel, such that so my error tolerance is epsilon. Yeah, so epsilon is my error tolerance. So the aim is n is given, the channel is given, and the error epsilon is given. So we want to construct an encoder and decoder which maximizes this rate R. So that's the task that you have to settle. And now the classical capacity of the quantum channel is precisely this. I mean, the maximum rate R that I can push through with correctness greater than or equal to 1 minus epsilon for all. Okay. Okay, so let's try to make sense of this. So let's prove the converse. So as you have seen in the classical one-shot version of this problem, the converse was very easy to prove. So the same thing is true out here. Okay. So So I claim that R is less than max
DH.
Yeah, over what I have to say, max
Input
over
distributions, right?
well, max over encodings n to rho m,
Oh, okay.
and I put I put probability distribution on m also. So I'm maximizing overall encodings, okay, and probability distribution on the input message PM. So this is I epsilon h, okay, n, and mm, actually, let's just second. This is true, but I'm just wondering if I can write something slightly better. No, let's keep it this way. So, yeah. Okay, so what is the state rho I'm doing? So state rho is a classical quantum state. So it's a state on the system MB. So it's sum over n, Pm, ket bra m. Okay, and this is rho B. So basically to define the state rho MB, I have to fix a probability distribution on M. Then I have to fix this encoding from the message to the density matrix on the input wire A. So this is M going to rho AM. And then the channel will act on rho AM and will convert it to rho BM. Okay. So this defines the CQ state like this. And over this CQ state, I can talk of the smooth hypothesis testing mutual information, which we know how to define in there. Okay, and then R is, yeah, you have some question.
We are completely bypassing the alphabet in this definition.
No, you are not completely bypassing the alphabet because it's an encoding from M to rho A.
So, I mean, usually we say messages to alphabet and then alphabet to quantum
Yeah.
state.
So it doesn't, yeah. So
And the mutual
yeah, I mean,
information is from alphabet to.
Yeah, you can do that, but here the alphabet and the messages are the same.
Message is the same. Okay, I see.
Yeah, I mean, you can take that viewpoint also. Sure.
So here we like usually when we do this, we have some assumption on the message space, right? I mean, some uniform distribution assumption. We don't have that here.
No, I don't have that out here. So yeah, so when we do the achievability, we will take the uniform distribution messages, then we look at the average error overall messages, and then the usual expurgation step will make it error for make that the error is small for every message at a slight loss of the rate. Okay. So, but that's in the achievability part. In the converse, yes, I'm putting an arbitrary probability distribution.
Oh.
Okay, it's just basically to match the achievability. I mean, if you look at the achievability, you'll also see an arbitrary probability distribution out here. Okay, and yeah, so to basically match the achievability, I'm just putting it this way. But you're right. I mean, in the course of the proof of the converse, the only distribution. Well, I mean, yeah. So we'll see the proof of the converse, but definitely, I mean, an important case is when I put the uniform probability distribution messages. But the statement as it stands is correct, and this is very similar to the achievability formula also. The achievability will basically be this minus some log 1 by epsilon kind of additive factors.
But Pranav, the achievability cannot be this. There will not be like the maximization over distributions on M, right?
Well, so think of a new sample space M. Yeah. So the way to do it is that when I'm talking of the converse, don't think of M, okay,
As a
as
message.
the message set. So
Okay,
that may
okay, I
confuse.
see. So you're pretty much like treating the message space as the symbol space and say, okay, screw it. So okay, okay, I see.
Yeah. So think of M as a new sample space. Okay.
Yeah, got it, got it. Thanks.
So think of M as a new sample space. Okay. So, and I mean, of whatever cardinality it is, I've not put any cardinality bounds. So think of M as a new sample space. We can put cardinality bounds later. So take a new set M, put a probability distribution Pm on that. Okay. Fix your encoding from little m to rho A of M. Okay. And now you get a CQ state, rho MB. Define the smooth hypothesis testing mutual information, and then maximize over rho m and this encodings. So this is the statement of the converse. Okay. So let's finish the proof and then we'll stop. Okay. So let us see. So put uniform. The proof is very similar to what we saw classically. Put uniform probability distribution on M. So now think of M as the message space. Okay. And now, so what did I get? I started with M, then it went to A, then it went to B, and then it went to M hat. So here is the uniform probability distribution out here. So let's say U of M.
So are you proving the converse now?
Yeah.
Okay.
Yeah.
But converse, you're assuming that there is a uniform distribution.
So the proof starts off by taking
yeah,
M
because
to be the
otherwise
message
you won't
space.
be able to put a bound on the M, like the absolute size of M, right? If you don't do that.
Yeah. So now, so what I've got, okay, and now I mean this the cardinality of M is 2 to the R. Okay, so R is the rate. Now what do I have? I have, okay, so now let me look at the probability distribution on M comma M hat, which is coming out of this entire process. Okay, resulting probability distribution. Entire process means put the uniform distribution M, pass it to the encoding, pass it to the channel, pass it to the decoding, get M. And now look at the tensor product of the two marginals. So this I know is uniform, right? So UM, and this is something arbitrary. I don't know what it is. So as you've seen before, so I know R is
বাবুলাল দোকানে বসে আছে, ও ওকে মাল দেবে না যতক্ষণ না পয়সাটা তুমি ট্রান্সফার করবে। আমি বললাম 1টা বাজে ছেড়ে দাও, তোমার তো শেষ হচ্ছে না।
okay. So actually, let's finish this proof next class. Actually, turns out I have to go now. Okay.
So yeah, I mean this
Yeah.
will take time, right? I mean we need to do the data processing and
Yeah, it will take a little bit of time. It's best we, I mean, restart from this point.
okay.
সরি বলার জন্য 1টা বাজে, 12:58 বাবুলাল বসে আছে।
So I'll stop now and we will resume on Tuesday.
Pranab, can you spare 10 minutes at some point today? Not now, but at some point
Yeah.
today. I need
Okay.
to discuss something. I mean, I'm just let me know, then I'll call you maybe.
Okay. Yeah. Sure. So in the evening, that's it.
Yeah, sure.
Yeah.
Okay.
Okay. Bye.
Bye.